Good afternoon and welcome to the sixth and final press conference at this 234th meeting of the American Astronomical Society in St. Louis, Missouri. I'm Rick Fienberg, I'm the AAS press officer. Assisting me this afternoon, monitoring our webcast, is the Solar Physics Division press officer, Trey Winter, and helping out with the Q&A also by handling the roving mic will be my colleague at the AAS, the editor of AAS Nova, Susanna Kohler. I'd like to ask you all to please silence your cell phones or anything else you have that might beep. And I want to mention that at the end of the briefing, we'll be pushing out a press release about the first of the three presentations this afternoon, so you can watch for that in your AAS press list email box. So all of the press releases and briefing presentations up to this point are linked from the press kit. So go to the press information page and you can find those. The video from this morning will be posted after this, and the video from this afternoon will be posted after this. So by the end of the day, all of the material should be online. Okay, so this is the first all-new topic in a couple of briefings. The last three almost, have focused on combinations of solar physics and Milky Way galactic results. This one we're going way out to the edge of the visible universe. We're going to talk about cold quasars, and we're going to talk about hot cosmology, by which I really mean a particularly hot topic in cosmology that I'm sure you will recognize once you start hearing about it. We're going to have three presentations. In order, they will be Allison Kirkpatrick from the University of Kansas on a new population of cold quasars. Then William Darcy Kenworthy from Johns Hopkins will talk about he will describe how local structure does not impact measurement of the Hubble Constant. And then Maurice van Putten from Sejong University in Korea will describe how Lambda cold dark matter, the current standard cosmological model, is in tension with data from a project called Pantheon. Now, if this is your first briefing, I just want to let you know that we will have all the presentations in order, and then at the end, we'll have the Q&A. So hold your questions until the end, and then we'll come back and do that. All right, so with that, I'll turn it over to Allison.
Okay. All right. Good afternoon. Thank you all for being here. I am going to present research that I have been working on for the past couple of years, and that is also being showcased in a poster today by one of my students, Brandon Coleman. So this is a new population of galaxies that we are calling cold quasars, that I've subtitled Nature's Jekyll and Hyde, and I hope to convince you of why that is the case. So I myself am a supermassive black hole hunter. I go looking for black holes in the very distant universe. It's particularly dust-enshrouded black holes. And quasars are the most massive of these, and they live in the most massive galaxies. The life cycle of massive galaxies is a dramatic story in which two disk galaxies collide, much like our own Milky Way is going to collide with Andromeda. This collision causes upheaval in the gas, pushing this gas towards the center of the galaxies. And at the center of every massive galaxy is a supermassive black hole. And as this gas gets pushed towards the center, these black holes turn on. They begin to rapidly feed on all of the gas around them, and this feeding superheats the gas, moves it towards relativistic speeds, and can cause feedback into the host galaxy as these two black holes now merge and become one. This is the quasar stage. Quasars are the most luminous objects in the universe. They are the most active of galactic nuclei. We also refer to active galactic nuclei as AGN. Quasars are almost universally produced by major mergers. Initially, as galaxies start to collide, we will see two active galactic nuclei, or AGN, as gas is funneled towards the center. We see X-rays, which come from a corona of gas right around the feeding black hole. as all of this gas from these merging galaxies is pushed towards the center, it obscures the X-rays and the black holes and hides them from view. And now we can only detect them in the infrared. And indeed, they stay in this state, this hidden state, as they merge into one supermassive black hole and as your galaxies merge into one giant galaxy. And then now we have what is called a dust-reddened quasar. It is a very massive black hole, actively growing, but hidden from view by gas and dust. Then, this superheated gas around this feeding black hole will launch winds and jets of material into the host and blow out all of the gas and dust. And now we see a luminous blue quasar. After this phase, your galaxy enters essentially stellar death. We say that a galaxy has died when it is no longer forming stars. We believe that for massive galaxies, it is the supermassive black hole at the center that kills them. Now, we have inferred that this is the life cycle of galaxies. We have inferred that dust-reddened quasars become luminous blue quasars. We've inferred that they expel all of the gas and dust. But this transition is a missing link. Transitioning quasars have never been observed until now. These quasars are transitioning. We undertook a survey of the sky of about 16 square degrees that we did with XMM Newton. We found the most luminous quasars, there are about 1,600 of them in the sky. And of these 1,600, 22, the 22 seen here, have a lot of dust and cold gas in them. These quasars are all located about 6 to 12 billion light years away when the universe was less than half of its current age, and we believe that they are actively quenching their host galaxies. Now, these images probably don't look like much because quasars usually don't look like much. So I'm going to focus on just one little one. This one here is my favorite. This galaxy is one of the most luminous X-ray sources in the sky. I listed the X-ray luminosity, 10 to the 46 ergs per second. To put that number into perspective for you, it would be the equivalent of 10 trillion suns shining on the Earth. Okay, so it's quite hot. This is an optical image. It's blue. Because it's blue, we know that it can't have gas and dust right around it. It can only have accretion. That's what's powering the blue light. And then beyond that, anywhere near the quasar, we can't have any gas and dust. Otherwise, you would see red. It's like when the sun begins to set, as it travels through more and more of the atmosphere, the light gets shifted to the red. Okay. However, normally when you see a blue point source like this, and you see a lot of X-rays, that's it. We assume that star formation is over in the galaxy. We assume that the galaxy doesn't have much gas and dust left. And yet, when we go looking at the sky with the Herschel Space Telescope, which looks in the far infrared, we see is this red dot. Again, doesn't look like a whole lot, but this little guy is the brightest source in our Herschel swath of the sky as well. This galaxy has 100 times more dust in it than the Milky Way. So it is an incredibly luminous X-ray source with a lot of dust. Now, due to the resolution of our telescope, we can't really tell what's going on in the galaxy, but we expect that if we could zoom in, it would look like this. That what we would see is the quasar at the center that has cleared out its gas and dust, and there would still be a ring of dust and gas further out that is forming stars, but it can't be sustained for much longer. We suspect that there is winds moving through the galaxy that is going to clear the host of the rest of the gas and dust and move this into its passive elliptical phase. So to summarize, prior to now, quasars that had dust were red, like that, because that dust was spatially located right around the quasar itself. And quasars that did not have dust were blue. But we have found 4% in our sample that are blue quasars that still have their dust. It's just further out, so it's not obscuring the color. This new population of cold quasars are rare, incredibly rare, very short-lived. It's a transition phase as the galaxy rids itself of the fuel to make stars, and soon this galaxy will enter the passive retirement of its life. Thank you.
All right, so my name is Darcy Kenworthy, and I'm here to talk to you about the Hubble tension and a possible solution to it, cosmic voids, and whether or not that can work. So what exactly is the Hubble constant? So the universe has been expanding ever since, well, I can't get the movie to start playing. Oh, there it goes. Oh, there it goes. All right. So the universe has been expanding ever since the Big Bang. As space expands, galaxies get further and further apart. And as light from those galaxies travels towards us, it gets stretched out by that expansion and reddens in color. The amount of redshift that we get and the relation to the distance away from us tells us the Hubble constant, which is the rate of that expansion. In order to measure the Hubble constant, the best way to do this in the local universe is to use supernova type 1a. So a supernova 1a is an enormous explosion at the end of a star's life. And these are interesting to us because they are standardizable candles. We can correct them to a standard luminosity. The dimmer the corrected brightness of a supernova is, the further away from us it is. Making a plot of the distance of the supernova against its redshift, like the one on the right, tells us the Hubble constant. So what is the Hubble tension? The Hubble tension is a problem that's emerged in the last 5 years or so, where the SHOES team, which has made the most recent measurements of the Hubble constant in the local universe, has found that the constant should be about 74 kilometers per second per megaparsec, while the Planck collaboration has predicted that the Hubble constant should be 67.4 kilometers per second per megaparsec based on the cosmic microwave background. This is now a 9% difference, and these measurements are 4.4 sigma apart from one another, which is greater than we can really attribute to chance. This is even more interesting because what we're seeing is these kind of two camps emerging. There are a bunch of measurements from the early universe that seem to agree better with Planck, and there's a bunch of measurements from the late universe that seem to agree with the SHOES result. So this is indicating, maybe, that this isn't a mistake in one measurement or the other, but rather new physics that we don't understand yet. So one thing that people have suggested to resolve this is, could the Milky Way lie in an underdense region of space, a void? The SHOES measurement is based on the nearby universe, and if this nearby region has less mass, fewer galaxies, there will be less gravity to hold things together, which means that the Hubble constant, as we measured it, would appear to be higher. In this plot, this gray region would expand faster than the rest of the universe. Several studies, Keenan, Barger, and Cowie 2013, and Whitburn and Shanks 2014 in particular, have found these voids extending to hundreds of megaparsecs, which is potentially large enough to affect our measurement, although these studies are based on a minority of the sky. So how can we test this proposed solution using supernova 1a? And the answer is we can check if supernovae nearby are too bright or too close than we would expect. My work, we combined several supernova samples together to get the largest sample of spectroscopic supernova 1a used in any analysis to date. More than 1,000 at relevant redshifts and 1,300 in the entire sample. We can measure H0 for each supernova and look for a step or a jump like the one in the plot to the right. And we can section our supernova dataset into two sets and look for that difference. So in this diagram, I've basically subtracted out that flat line so that we can just see variation in the Hubble constant as a function of redshift. Each one of these points represents about 80 supernovae. We don't really see any evidence that the Hubble constant is evolving at higher redshifts as compared to low redshifts. The red line down here shows the amount of change in the Hubble constant that we would need in order to resolve this Hubble tension through a local void. And the blue shading shows the amount of uncertainty in the local Hubble constant we would expect from standard cosmology. There's very little variation here, not enough to bridge that gap between Shoes and Planck. We also do the thing that I suggested we could do a few slides ago. We split our data set into two groups, a low redshift group and a high redshift group at this redshift Z split, and vary that bin edge, looking for whether there's any place in our sample where the Hubble constant goes from a high value to a low value, which could potentially indicate the edge of one of these cosmic voids. And what we find is that there are not any significant sections in our sample. And in fact, we find that we can reject these proposed local voids at 4 sigma in the case of Whitburn and Shanks 2014, and at more than 5 sigma in the case of Keenan, Barger, and Cowie 2013. So we conclude that our result is not being affected by any form of local structure, and our precision in the conclusion is 0.6%, which is a lot smaller than the 1.9% uncertainty of the current Shoes best estimate and the 9% difference between the Shoes estimate and the prediction of Planck. A void large enough to resolve that Hubble tension would also be theoretically disfavored under standard cosmology at more than 20 sigma. And there are, as I mentioned earlier, these independent measurements. In particular, the Holy Cow measurement is very comparable to ours, but it is entirely unaffected by these effects of local structure. Looking at the state of the field, it looked more and more like there are new physics at play which are not understood at the moment.
Okay, so I'll be talking about originally Lambda CDM is in tension with Pantheon data. That is part of my talk, but I've simplified the title, partly because of my jet lag of 12 hours, to a simplified title, Alleviating Tension Between Lambda CDM and the Local Distance Ladder from First Principles with No Free Parameters. So this is motivated by the H-not-tension problem, as nicely introduced by our previous speaker. And what I would first like to highlight is some complementary pictures to this to illustrate the origin of this tension. This tension doesn't come, well, it comes out of the blue in some sense, but it comes out of a huge bodies of work by two very major groups. The first group is the group around the Planck satellite, measuring the CMB in as high angular and temperature detail as we possibly can with current technology. And the other one is the people who are pursuing supernovae in the local universe and measuring the Hubble parameter on the basis of using them as standard candles, as explained by the previous speaker. Now, there is a fundamental difference in extracting cosmological parameters from the two. In the analysis of the CMB, by Planck, people are using as a standard approach the so-called Lambda CDM model. So it's a model-dependent analysis of an otherwise model-independent observation of this distribution of the microwave background, as you see in this image. And on the other hand, you have on the right, you have a model-independent local observation, very direct to the true nature of the Hubble parameter, namely receding velocities as measured by redshift. And so you're actually making a bit of a tricky comparison. One is a model-dependent measurement, and the other one is a model-independent measurement. So in some sense, one should not be surprised that some tension will appear. In some sense, you can think of the Planck analysis as measuring h naught through 1 over h naught, and the measurement by supernovae as being a direct measurement based on Doppler effects. So, but the numbers that come out are becoming much more interesting now as they become more and more precise. You see them listed here. And if you compare them, and this is sort of a standard way advertised by Rees, is you simply look at delta H between these. So this delta is not an error, it's a discrepancy as you observe between these two approaches, and normalize it to the, say, mean value. Then the result today is a 9% discrepancy, plus or minus 2%. Okay, so this is, so now you can ask, should we worry about this or not? And there are many comparisons also historically that would illustrate this. If you go back to the earlier times of last century, we had Mercury and the precession of Mercury. It was a small effect. Well, today it's still a small effect. It doesn't change. It's very persistent, and it is the persistence and not being able to explain it by more kitchen and garden origins that made it significant. And ultimately, it turned out to be a shimmer of an enormous wealth of new physics, as we now refer to as the theory of general relativity. So one should be very careful in interpreting a result like this. It could be very important. It could be just a very similar shimmer of new physics. So the question is very much justified with this historical perspective in mind. Is this potentially new physics? And now you can add beyond lambda CDM, because the Planck analysis was based on lambda CDM, and these supernova surveys on purpose do not assume any cosmological model. So then you should ask, what is the sweet spot in lambda CDM? It's actually a non-trivial question. What is the most questionable assumption in lambda CDM? After all, lambda CDM is created by hand. Well, if you ask different people, I invite you to do so, you will get different answers. But my answer is, it has a problem in the future, or it has a potential, of course, problem in the future. Namely, that lambda CDM predicts that in the distant future we live in a pure de Sitter state. And the de Sitter state is defined as having a constant Hubble parameter. Well, that is really the result of creating a framework by hand. And you have to be very careful in physics, because such a statement may be threatened by quantum mechanical anomalies. In other words, is this de Sitter state stable? So lambda CDM assumes it is stable, but maybe it is destabilized by quantum mechanical anomalies. Now, there is an interesting observation one can make. We live in, as taught by Hubble and Lemaitre, we live in a universe that has a Big Bang, or in the past. And we also teach, usually not referring to the Big Bang, that if you do an experiment today and tomorrow and yesterday, you get the same results. It's called Poincare invariance, in this case specific to time translation. But what if you take your time translation to be 1 over a Hubble time, and especially negative? Then, of course, it gets a bit absurd, because you're proposing to do an experiment before the Big Bang. So the notion that the Poincare symmetry is truly preserved in the universe is simply not true in the face of a Big Bang. If you break a symmetry, particle physicists will tell you it comes with, especially if it's a symmetry broken related to time symmetry, it will actually come with a new energy scale, a low energy scale, if you talk about breaking the symmetry in a ground state. And in this case then, a very specific low energy scale comes directly out of this, which is the Hubble parameter times the Planck constant. I didn't write it down because I wanted to minimize my equations. That's a very small energy. However, you then should ask, can that conceivably be an origin of the dark energy that we observe? Well, if you simply take the total dark energy in the universe within the cosmological horizon, you can do the integration basically on the order of the closure density times the volume, which of course is not a small amount of energy. So then the question is a counting question. How many degrees of freedom do I need where each degree of freedom has an energy Hubble parameter times Planck constant in order to then account for the total dark energy in the universe. That becomes a dimensionality question. Do we live in a universe with effectively a geometric dimension of phase space 1, 2, or 3? If you choose 3, it's kind of like a Zeldovich picture, and you get into the usual problem of a UV divergence of dark energy coming out of quantum field theory. But what about if you choose 2, or maybe 1? Well, if you choose 1, you get too little energy, so that's ruled out as well. What about 2? 2 refers to simply taking a Planck distribution of degrees of freedom over the cosmological horizon. And lo and behold, that gives the correct summation of those small energies. Okay, so we should take that potentially seriously, that we have a low energy excitation of Planck scale fundamental degrees of freedom distributed over the cosmological horizon. Now, if we want to make a connection to a quantum mechanical origin more formally, we wish to formalize this approach in order to get an explicit expression. We could turn, say, to the Feynman path integral formulation. That's a very powerful formulation that, after all, on the one hand, respects the notion that general relativity is defined in a geometric optics limit, and at the same time must be connected to some quantum mechanical picture through this propagator, which he introduced as e to the is over h bar. Now, e to the is over h bar works very nicely if you're a particle physics working at CERN, because then your background is a Minkowski space-time. And that has a trivial infinity, literally at infinity, where things are trivial and null and there's no gravity. But we don't live in a Minkowski space-time if we think about our universe. We live in an FRW space-time with a cosmological horizon. So infinity is non-existent, and in fact, large distance behavior is non-trivial as you run into this cosmological horizon. So what do? If you think about ES over h bar, then IS over h bar is a total phase. Of course, total phase, as we all know from quantum mechanics by itself, is not meaningful. It has to be a phase reference. And again, if you switch back to Minkowski space-time, your infinity, your large distance behavior will naturally give you a 0 phase reference. But now we run into, as mentioned, the cosmological horizon. That may have a non-trivial phase reference, unless, of course, you're in a radiation-dominated regime, in which case you degenerate everything back to Minkowski. But we don't live today in a radiation-dominated regime. So what we need to do is to define a proper phase reference as not, or IS not over h bar, that is dictated by the cosmological horizon. So you can do this equivalently through a energy density that by natural covariant arguments must be generated by the Ricci tensor, in this case then of course restricted to the geometric structure of the cosmological horizon. If you follow this route, it's a little bit technical, you get an explicit expression, 1 minus qh squared, which people working in cosmology will recognize as the q being the deceleration parameter and h being the Hubble parameter. What is important here is that you get an expression that has no free parameters. These are canonical FRW parameters of late-time cosmology. I'm not adding anything new. So I'm exploiting some basic principles to construct something with no free parameters. Okay, so what happens if you stick this energy source in the FRW equations, which are essentially a reduced system directly from the Einstein equations, but specific to isotropic homogeneous and so forth, in order to make life manageable for the theorist, and which in fact works very well observationally on the largest scales. Then actually you're introducing a source term that has then its own manifestation in the evolution of the Hubble parameter. And then you get this formula. It's an analytic solution in response to this lambda being 1 minus qh squared. And it has many interesting properties. At high z, it's essentially lambda CDM. And the differences in behavior, departures from lambda CDM, by the way, this is not a perturbation of lambda CDM because there is no continuation parameter between the two models. So, but anyhow, so at modest z, and especially negative z, differences with lambda CDM become strongly manifest. In particular, if you take z to be negative, you will discover that the de Sitter state is unstable, which is what I anticipated when you talk about is it threatened or not by quantum mechanical anomalies. So let's compare now with Lambda CDM, which is the second formula below here. You will recognize that they have the same parameters. You have H naught, which is just a scale parameter setting the total age of the universe. And you have this little omega m, which is the matter content normalized to closure density today. So those are just two numbers. So, the invitation one has now is to take these two different formulas with unknown parameters h naught and omega m and see how it plays out with the data. And then you're literally comparing apples with data and ask which fits better. That's an honest game you can play. So we did that, and here you see four numbers, and on the top you see a couple of pictures with data that were compiled by Farouk et al. On the Hubble parameter measured by different ways over a finite range of redshift. So you can fit these data by these two different models and ask a simple question, which one fits better? So the one with the unstable de Sitter state in the future gives you 74.9 plus or minus 2.6. The errors are a little bit bigger than, of course, what Maurice is advertising, but it's the magic 74 comes out quite nicely. If you use Lambda CDM, you get the lower value, 66.9. And of course, if you look on the right for reference, I reiterated here the latest Maurice value, 74, and the Planck value based on a Lambda CDM analysis of the CMB, 67. So you see that these numbers are essentially the same. The errors are a little bit different because we're using different data sets, but they're well separated, and quantitatively they are essentially the same, statistically, fully consistent. So one is in fact now reproducing the canonical H-naught tension problem by simply comparing two different models against a given data set. So this is my conclusion, that if you follow strictly the rules of low energy quantum gravity and you do proper counting of dimensionality of the true phase space of FRW universes, and you're very careful about treating infinity by taking into account phase reference induced by cosmological horizon and all those sort of theoretical details, you get an explicit expression for lambda. There's no free parameters, so you can simply ask the question, does it work or does it not work? And ultimately the data should be the final referee in this. So, and having then two models with the two same parameters, you can ask, does this unstable de Sitter future alleviate the tension? The answer is, well, you can see it here in green. You get essentially the same delta H over H. So Rees determined 9% plus or minus 2, and from the data I used, okay, I get about 10% plus or minus 4%, completely consistent. If you take the Pantheon data set, which is this very nice data set briefly alluded to earlier, that is continuously extending to more and more supernovae, then you find indeed if you also do a test on omega m estimate, then the omega m for lambda CDM is more than 4 sigma, and then it reduces to a much more relaxed tension of 2.5. It's not a perfect tension-free result, but it is much less than that of lambda CDM. So the conclusion is, if you ask about this H-naught tension problem, are we looking at new physics? The answer is yes, potentially, but in a subtle way. It's probably a message from the future in the sense that lambda CDM will break down in the future through its de Sitter state being ruled out by quantum mechanical anomalies. And of course, if lambda CDM is ruled out in the future, it cannot hold true to all orders today by analyticity. So in a subtle way, the future is telling us that there should be tension today. And you can, as I did here in this brief talk, formalize everything in exact analytic solutions. So thank you.
Wow. Well, I'm glad I didn't see anybody's head explode. Very interesting stuff going on here. And I would like to throw it open to questions. There's got to be some. So what we're going to do is, Susanna, can you grab the mic? We're going to wait for the microphone. Tell us who you are and who you're affiliated with and who you're asking your question of. And if you're on the webcast, please queue up your questions via the text chat so that Trey can relay them to us. Go ahead.
Hi, Daniel Deveau, Canada, France, Hawaii Telescope. My question is for William. In the graph that you showed of the evolution of the measurement of H0 over time, the shoe measurement, the local measurements seem fairly smooth, and there's a big break in the Planck measurement. What does that due to? Did they change something in the Planck analysis, or was there some systematic that was taken care, that was introduced?
Oh, you're talking about the one showing measurements over time.
Yes, you know, you have these two areas, and you see the error bars getting smaller, and the local measurement seems pretty smooth, but the Planck one at some point just breaks up, and I've always wondered, where does that come from?
Is it? It's not this.
No.
Next slide, I think.
Next one.
Yeah, that one.
Okay.
Yeah.
Yeah, so that is, those first set of red points from the cosmic microwave background are all WMAP measurements. And then from there, the rest of them are Planck. And you can see that there was a drop from something around 70 for WMAP to something more around 67 for Planck. I don't understand that very well, but Planck has verified their results. They're pretty sure that that's the true value, and there are a number of other checks that you can do with other cosmic microwave background data sets, or even independent of the cosmic microwave background, but still based on the early universe, and you still get something that's about 67.
You may recall that the recipe for the universe, what fraction is dark energy, dark matter, and ordinary matter, changed a little bit from the WMAP result to the Planck result. So, Planck was a higher resolution, more sensitive experiment, and it got, slightly different, but presumably more accurate results. Any other questions here? I have some, but let's see if we have any online first. Nothing online yet? Okay. So I wanted to start with Allison. So you found 4% of your sample, this 22 of these quasars that appear to be in transition from one state to another. Now, had there ever been any found before, or are all of these the first to be found?
I am not aware of blue quasars that have been found with that amount of cold dust in them. Certainly red quasars are known to have far infrared emission, but the blue ones, I don't know of any off my top of my head.
Okay, so this really is a new kind of object in a sense.
Yes.
Okay. And then for Darcy, I was wondering if you, let me see, how did I want it? Oh yeah, let's see. You're concluding that you're concluding that the most common, or at least one of the most common possible explanations for the tension that doesn't involve new physics is the local void issue. And you've pretty well ruled that out. Can you tell us if there are other proposed explanations that don't involve new physics, and whether you've been able to address those at all?
So in terms of the shoes measurement, which is what I know about best, there have been, we're pretty confident that we've identified possible systematics in our data set and accounted for them. These things that could bias our measurement to one side or another. And there have been reanalyses by other groups using our same data set that have also come to the same result. And we've done a number of different analyses ourselves, checking what if we use only this set of supernova or this set. And it's all come out pretty consistent. So I think that most of the known systematics at this point at our end of the distance ladder have been more or less ruled out. And at the other end, the Planck team, as I said, there are a number of experiments on both ends of this that have found similar results, but there's this big gap between these two camps. So to me, that is really strong evidence that you can't have just one systematic that resolves this whole thing. you would have to have a conspiracy of errors or new physics.
Okay. But or this idea of the void causing, well, that would be a systematic error, I suppose, right? And once you account for that. So what I was getting at was, has anybody come up with any other possible physical explanation, besides voids,
Well,
that don't, before they say, well, it's got to be something that we just haven't thought of yet?
not that I'm aware of that
Okay.
aren't new physics. Not that
Okay.
of,
Yeah. Okay, and now I want to try to get my head around Maurice's results. It sounds to me like the fact that the universe is evolving is key here. The fact that it's different in the past.
Right. If you had an
Will be
eternal
different in the
universe,
future.
Right. You couldn't use my first argument.
Okay.
Yeah. Because then there's no Big Bang.
Right. So that's a critical component. The fact that there's a horizon caused by the finite age of the universe is part of this. So the machinations you're doing with the equations are in that context. Okay, so you haven't introduced anything there that's new.
No, there's no magic.
Yeah.
No.
So if I heard you say the phrase quantum gravity, I think, once or twice.
Cosmology, yeah.
And I'm not a cosmologist, but I try to stay up on this, and I know that one of the phrases you hear a lot is, we need to figure out how to reconcile quantum physics with general relativity, that right now there is no real theory of quantum gravity. So can you clarify a little bit about how you're approaching that, or because you talked about quantum mechanical anomalies, and you talked about Lambda CDM, which is basically general relativity with a cosmological constant. So I just wondered if you could clarify a little bit about what you're doing to either reconcile those, or what the role of quantum mechanics is.
Well, I mean, the simplest way, as you know, there's so many different ways to talk about quantum mechanics, but inevitably, when you talk about quantum mechanics, there's an H-bar somewhere, right? It's hard to talk about quantum mechanics without
And
H-bar.
and just to make sure we're all understanding what you're saying.
Yeah, Heisenberg constant. Planck's constant. Yeah.
Okay, so there's a very, very small physical scale beyond which you can't.
Well,
really...
but it's a very peculiar scale, right? It's a unit of action. It's energy times time. It's momentum times. It's a non-trivial dimension full fundamental constant. Mm-hmm. It took a brilliant person to come up with H-bar, obviously, but it has this unique feature that it can introduce features that you do not expect based on classical arguments. That's why they developed quantum mechanics based on atomic questions coming out of atoms. So in this case, so I start with an argument that fairly naturally, I'm not doing anything really out of the ordinary, except on a Hubble scale, working on a Hubble scale, to say that there is a natural origin of at least some energy, and you should call it perhaps indeed dark energy, coming straight out of the box. Once you realize there's a Big Bang, you break Poincare symmetry. But then, of course, that's very cute that you can sort of use it in an undergraduate teaching. But of course, the serious question, if you want to confront with data, you have to go much further, because you need some exact solutions. I mean, otherwise you cannot. You don't want to be freewheeling at that point. So to formalize it, you have, and then the related question the question to be answered by a formalization is this energy stable or not? Because that is not answered by this scaling argument. Mm-hmm. So the first jump into the world of quantum mechanics is by this argument. We have essentially a background energy per degree of freedom, which is the Hubble parameter times Planck's constant. Okay, that's fair enough. It's an enormously small energy, but then again, the universe is enormously large, so we might be looking at a very large number of degrees of freedom. And actually, a convenient way to express that number is just to talk about the geometric dimension. You can give a true number; it's on the order of 10 to the 120, but it doesn't really mean much. It's more than a Google, so to speak. Mm-hmm. But that's why I use just dimensionality. Is it maybe a ring that is holding all the Planck length units, or is it an area, or is it the volume? So Czeldowicz took the volume, and then you get into all sorts of trouble. You get too much. If it's a ring, it's too little. And if it's an area like the Hubble area, you get the exact correct scaling. Okay, but anyway, then you need to go further And then h bar is not enough. You need to do something like use Feynman's path integral formula, which if you think about it, is really an amazing, ingenious concept, because it is merging the notion of a geometric optics limit, which is sort of another way of saying classical theory, and anything that is not the geometric optics limit, which then you automatically fall back to quantum mechanics. That's what it does. But to apply it then on a proper background, you have to worry about infinity. So then all of a sudden, this other guy, Mach, comes into play, which was also a very smart guy, predecessor of Einstein, who actually confronted Einstein with how do you worry about, how do you define inertia and all those things, which was never really properly answered. Mm-hmm. But anyway, infinity is important. It's trivial in Minkowski space-time. So normally you just write e to the is over h bar and you don't worry about it. But now, again, in the face of the cosmological horizon, you have an additional feature to worry about.
So are you making a prediction about the behavior of dark energy? Like people are arguing whether it's the cosmological constant or whether it changes with time.
Yeah.
Measurements of the equation of state seem to suggest that it seems constant with time, but
No,
there are all these
incom-
surveys being done.
Yeah,
So are
yeah,
you going to
yeah.
see, is there going to be a result from the dark energy survey or the dark energy spectroscopic instrument or any of these other things that you're going to be able to point to and say, this is evidence of what I'm suggesting?
Well, I have this explicit expression for lambda, which is 8 pi times the dark energy density. It's 1 minus q h squared. There's no free parameter. So
Yeah.
either it works or it doesn't. I mean, this line of discrete theory arguments gives you this. Let's see what happens.
Okay.
It's fair
will
game,
that,
right?
and will that number?
Well,
that
so
number will
far, it nicely accounts quantitatively for the
Okay.
existing H0 tension. I find it
Yeah.
sufficiently encouraging to, give my talk here earlier today.
Right. No, okay. So,
So yes, it is
So-
dynamic, and
Right.
it is zero in the radiation-dominated regime. It includes the matter-dominated regime, and Q is 1/2. There is a little expression I didn't show for the W parameter, and the equation of state parameter is 2Q minus 1 over, I forgot, something else. But anyway, it's zero when Q is 1/2.
You can Google it.
It's zero
Yeah.
when Q is 1/2. That's important.
okay.
So it contains the matter-dominated regime.
So this isn't one of those theoretical results that, that we have no hope of testing. I mean, this is,
Well, I'm sort
Yeah,
of inviting
you're-
by giving a little demo. So
Yeah.
far, so good is sort of my statement. Maybe tomorrow there is somebody else who says,
Yeah.
well, it's good but not sufficient, right? That can happen.
Yeah.
But so far, so good.
okay, that's really interesting. Great. Have any other questions popped up?
Yes, Rick Lovett, freelance writer, has a question for Allison. Allison, is there a quasar in the future of the Milky Way from its collision with Andromeda? If so, when does that happen, and how would it affect planetary systems like ours? In other words, by looking into the distant past of other galaxies, are we looking at the distant future of our own?
Yes, that is a great question. Yes, we are. So there is a quasar in the Milky Way's future. There is a supermassive black hole in the Milky Way's future. So the Milky Way has a supermassive black hole now. It is rather anemic. It's not very interesting. Andromeda's, if it's possible, is even less interesting. When they collide, again, we got all this material just funneled into them. They will light up, they will merge into one black hole, and that will dominate our night sky, actually. They'll be incredibly bright. And so what we see now as the nice plane of the Milky Way will instead be this bright halo. And it'll be difficult to see all the Starlink satellites out there. So this will be
We'll
in
have our
about...
revenge eventually.
That's right.
Yeah.
This will be in about 3 to 4 billion years. So luckily for us on Earth, that'll be about the same time that the sun has turned into a red giant. So we'll have other problems occupying us at that point in time. But it will be the beginning of the end for life as we know it in the Milky Way. No new stars will form after that point because the quasar at the center of the Milky Way will superheat all the gas, blow everything out. Planets will probably survive, but you won't get anything new, and so they'll just be going around red dwarfs until they ultimately burn out.
Any follow-up there? No? Rick is crying into his computer back there in Oregon. I can hear it now. Any more questions here in the room? All right. Well then, we will thank our presenters again, and thank you all. Thank you all for showing up at the last press conference. There are no press conferences tomorrow. I want to announce the next press conference anyway. It will be in Honolulu. Now I made this diagram before they changed the schedule. The meeting actually is going to run from 4 to 8 January instead of 5 to 9 January. So the first press conference will be on Sunday, actually, the 5th, I guess, of January. But it'll be in Honolulu, so I'm sure you're all going to want to be there, especially if you live in a cold climate, because this is a meeting in January in Honolulu. So we hope to see you there. And enjoy the rest of the meeting. We still have all the rest of today and all of tomorrow morning. So don't go home yet.
Right.
All right. Thank you all very much.